Within the boundless expanse of cosmic night, a domain exists where the very fabric of space and time unravels. Here, the fundamental rules of physics surrender and reality contorts into forms beyond our comprehension. This phenomenon, this celestial behemoth, is what we term a black hole. But consider a staggering proposition. What if the entirety of your existence, the world you perceive, and the whole of the observable cosmos is, in fact, confined within the inescapable walls of such a cosmic dungeon? Groundbreaking observations from the James Webb Space Telescope have sent tremors through the foundations of astronomy, unveiling cosmic arrangements that defy the expectations of a randomly ordered universe. Brace yourself for an expedition that will question the very essence of your perceived reality. Our journey into this profound mystery begins now. Envision stepping through a portal that irrevocably slams shut behind you. This is the stark reality of crossing a black hole's event horizon, a threshold in space-time from which there is no retreat. It is a frontier where even light is ensnared in a perpetual spiral toward oblivion. The event horizon forms the ultimate point of no return, a spherical perimeter of fate encircling the most extreme entities in the cosmos. Yet, this is where the concept begins to warp the mind. The dimensions of this cosmic cell are dictated solely by the quantity of matter it consumes. If you double its mass, you consequently double its diameter. A tenfold increase in mass results in a black hole 10 times as large. This is not mere abstract arithmetic. It is a direct linear correlation observed across the universe, from the remnants of massive stars to the supermassive titans that anchor the hearts of galaxies. This leads to a truly astonishing calculation. When astrophysicists compute the total estimated mass of our observable universe and pose a direct query, what would be the size of a black hole capable of containing such an immense amount of matter? The result is breathtaking. The event horizon of such an object would span approximately 93 billion light-years, a figure that aligns almost perfectly with the boundary of our own cosmic horizon, the maximum distance from which light has had the chance to reach us since the dawn of time. This is more than a simple numerical curiosity. The average density of all matter contained within our cosmic horizon is precisely what one would anticipate finding inside a black hole of this colossal scale. It is as though our entire universe was meticulously gathered and compressed to the exact density required to trigger its own gravitational collapse. And yet, we seem to exist quite placidly inside this theoretical prison, oblivious to our confinement. The mathematical elegance deepens when one considers the predictions of Einstein's general relativity concerning the interior of a black hole. Instead of culminating in utter annihilation, the equations point to the possibility that an entirely new region of space-time blossoms on the other side of the collapse. Were you to somehow endure the passage through a black hole, you would witness the complete future history of the universe you departed from play out in an accelerated spectacle. Simultaneously, before you, a brand new cosmos would begin its own process of expansion and evolution. This possibility presents the most profound inquiry in contemporary cosmology. Could we be the inhabitants of that emergent new universe? Are we the descendants of an ancient cosmic implosion that transpired in a parent universe forever beyond our perception and reach? Our cosmos bears remarkable indications of having been born with highly specific initial conditions, including the precise values of its fundamental constants, a particular spatial geometry, and now, compelling evidence suggesting it may have even inherited the angular momentum of its progenitor. The ramifications of this idea extend far beyond the realm of academic thought. If our universe is truly contained within a black hole, then every black hole within our own cosmos could, in turn, be a vessel for its own fledgling universe, hermetically sealed from our own by the one-way nature of its event horizon. Entire civilizations, worlds beyond counting, and infinite possibilities could be flourishing just beyond those dark thresholds, perpetually concealed from our view yet undeniably real, thriving in their own pocket dimensions of reality. The tale of how we began to suspect our cosmic confinement starts with the work of a brilliant physicist, Roger Penrose, and a mathematical proof that appeared to finalize our destiny. In 1965, Penrose mathematically established that, under quite general circumstances, the process of gravitational collapse must unavoidably culminate in a singularity, a point where matter is crushed to an infinite density, and the laws of physics effectively surrender. This singularity theorem laid the groundwork for our modern comprehension of black holes, a concept later expanded upon by Stephen Hawking and his colleagues, who demonstrated that these mathematical monsters were not merely theoretical possibilities, but inevitable features of our universe. For many years, the scientific community accepted that any matter falling into a black hole would be compressed beyond all recognition, squashed into a point of zero volume, where time ceases and space is stripped of all meaning. However, Penrose's theorem was rooted in classical physics, the predictable realm of everyday experience. Once quantum mechanics is introduced into the scenario, the entire picture transforms. On the subatomic scale, particles defy classical conventions, displaying behaviors that appear utterly impossible from our macroscopic viewpoint. The quantum domain is governed by fundamentally different principles, among them the exclusion principle. This rule dictates that no two identical particles are permitted to occupy the same quantum state. It is nature's ultimate regulation against overcrowding. Particles possessing identical properties simply refuse to be squeezed into the same location, irrespective of the pressure applied. As matter collapses towards the center of a black hole, this quantum prohibition becomes supremely important. Recent mathematical models from researchers at the University of Portsmouth have unveiled something incredible. When quantum effects are correctly integrated into the mathematics of gravitational collapse, the presupposed singularity simply vanishes. Instead of crushing matter into oblivion, the collapse halts at a maximum density and then recoils, akin to a cosmic superball bouncing off an invisible wall with immense energy. This rebound does not necessitate any exotic new physics or hypothetical particles. It arises as a natural consequence of uniting Einstein's general relativity with fundamental quantum mechanics, two well-established and trusted pillars of modern physics. The equations demonstrate that as the collapsing matter nears the potential singularity, quantum pressure escalates until it overpowers the force of gravity, compelling the collapse to reverse its course. What springs forth from this cosmic rebound is extraordinary, a new, expanding universe with characteristics that strikingly resemble our own observable cosmos. The bounce naturally generates two distinct phases of accelerated expansion that closely mirror both the inflationary period of the early universe and the enigmatic dark energy that is currently accelerating its expansion. No speculative fields or unproven physics are needed. It is simply the unavoidable result of quantum mechanics forbidding infinite compression. This implies that our Big Bang might not have been the absolute beginning, but rather the moment of maximum compression that was succeeded by an explosive expansion within a cosmic cycle that could be eternal. We may not exist at the dawn of time, but perhaps in the midst of a perpetual dance between collapse and expansion, between endings and new beginnings. The universe that collapsed to forge our own has left its imprints everywhere, in the finely tuned values of physical constants, in the very geometry of space, and potentially in the collective spin direction of galaxies across the vastness of the observable universe. In the heartland of America, at Kansas State University, computer scientist Leora Shamir was on the verge of a discovery that would challenge the core tenets of cosmology. Utilizing images from the James Webb Space Telescope's Advanced Deep Extragalactic Survey, he was investigating a characteristic that ought to have been entirely random: the rotational direction of spiral galaxies as observed from our planet. In a universe governed by chance, one would anticipate that roughly 50% of all galaxies would spin in a clockwise direction and the other 50% counterclockwise. much like the results of flipping billions of coins. Any minor deviations would be attributed to statistical noise, insignificant fluctuations that would balance out over a sufficiently large sample. Yet, when Shamir analyzed 263 galaxies from the deep universe, he uncovered something that should not exist. A staggering 60% of these galaxies were rotating clockwise, with only 40% spinning counterclockwise. The statistical likelihood of this occurring by sheer chance was less than 7%, a result that is astronomically improbable in a cosmos assumed to be random. Something was imposing a preferred direction of rotation on the grandest scales imaginable, thereby violating our most fundamental assumptions regarding cosmic symmetry. This finding was not entirely without precedent. Earlier observations from ground-based telescopes had hinted at similar asymmetries, but the James Webb Space Telescope, with its unparalleled capacity to gaze into the distant universe, revealed this pattern with astonishing clarity. Even more compellingly, the asymmetry seemed to intensify when observing more distant galaxies, objects seen as they were billions of years ago when the cosmos was much younger. The pattern also exhibited another peculiar trait. The asymmetry was most pronounced near the galactic poles, the directions perpendicular to the disk of our own Milky Way galaxy. This finding suggested that whatever was instigating this preferred rotation had a distinct relationship with our own galaxy's orientation in space, as if a cosmic axis threaded through the universe, influencing the formation and evolution of galaxies. To eliminate human bias from his analysis, Shamir employed an automated computer program named Ganalyzer to classify the rotational direction of each galaxy. This program transforms galaxy images into radial intensity plots, which allows it to detect the curvature of spiral arms and thus determine the direction of rotation. This objective and reproducible methodology exposed the cosmic asymmetry with a mathematical precision that could be verified by any researcher. The consequences were profound. If galaxies truly exhibit a preference for one direction of rotation, it signifies that the universe is not isotropic. It does not appear the same in every direction. This directly contradicts the cosmological principle, a cornerstone assumption that underpins our understanding of cosmic evolution. The universe must possess some form of inherent asymmetry, a preferred axis or direction that has influenced the formation and spin of galaxies across billions of light years. But what could possibly generate such a large-scale preference? In our daily lives, objects spin because an external force imparts rotation to them. We witness this in phenomena ranging from ice skaters accelerating their spin by pulling in their arms to gas clouds collapsing under their own gravity. The principle of conservation of angular momentum dictates that any initial rotation is amplified as an object contracts. However, this does not explain why the universe itself might possess a preferred direction of spin. The solution may reside within the most extreme objects known to physics, black holes that rotate at incredible velocities and wield the power to shape space-time across immense distances. Every black hole in the cosmos spins. This is not a theoretical conjecture, but an observational reality etched into the very structure of space-time. When giant stars exhaust their fuel and collapse, they pass on their rotational momentum to the resulting black holes, amplifying it to unimaginable levels. The law of conservation of angular momentum converts a slowly turning stellar giant into a cosmic vortex of distorted space-time, spinning with such ferocity that it drags space and time along with it. But it is at this point that the narrative takes a truly mind-altering turn. According to the physics of black holes, only two properties can traverse the event horizon from the external universe: total mass and angular momentum. All other information, chemical makeup, temperature, magnetic fields, even the intricate history of the matter's formation, is utterly erased. The black hole simplifies into an object defined exclusively by its weight and its spin. If our universe is indeed situated inside a black hole, it must have inherited the angular momentum of the entity that collapsed to form it. This inherited spin would manifest as a cosmic axis, a preferential direction woven into the very fabric of space-time, which would then influence the motion of matter and the formation of galaxies throughout our observable cosmos. Consider it a form of cosmic genetics. In the same way that living organisms inherit characteristics from their parents, our universe would bear the rotational signature of its parent black hole. This inherited trait would be far too subtle to be noticeable in local physics or everyday phenomena. However, over cosmic distances and billions of years of evolution, this inherent spin could accumulate, resulting in the very asymmetry in galaxy rotation that the James Webb Telescope has detected. Theoretical physicist Nikodem Poplawski of the University of New Haven has been a proponent of this concept for years. In his model, matter falling into a black hole is not crushed into a singularity. Instead, quantum phenomena prevent infinite compression, causing the matter to rebound and expand into a new universe on the other side of the event horizon. This new cosmos would seem entirely isolated from its parent, connected only through the warped geometry of space-time. From our perspective, the parent universe would appear as a white hole, the theoretical inverse of a black hole, which expels matter and energy and cannot be entered from the outside. However, we could never directly observe this white hole, as it would exist beyond our cosmic horizon in regions of space-time that light from our universe is destined never to reach. This paints an awe-inspiring portrait of cosmic evolution. Every single black hole in our universe could be the genesis of a new cosmos, giving birth to baby universes that inherit the angular momentum and fundamental properties of their parents. These universes would be completely cut off from us, free to develop their own galaxies, stars, planets, and perhaps even life, all while being perpetually hidden behind the one-way barrier of the event horizon. The observed asymmetry in galaxy rotation thus becomes a fossilized record of our cosmic genesis, preserved across 138 billion years of universal evolution. It is the signature of our parent black hole, inscribed in the spin of galaxies across the entire observable universe, awaiting the day when creatures like us would develop telescopes powerful enough to decipher this ancient cosmic message. When the James Webb Space Telescope cast its golden gaze upon the cosmos in 2022, it marked more than just an improvement in astronomical instruments. It was a paradigm shift in our ability to witness cosmic history. This $10 billion observatory can delve deeper into space and further back in time than any device humanity has ever constructed, unveiling the universe as it was in its youth, a wild, tempestuous, and dramatically different place from the one we know today. The telescope's unmatched infrared sensitivity enables it to penetrate through cosmic dust clouds and capture the light from the very first galaxies that coalesced after the Big Bang. But the true strength of James Webb lies in its capacity to resolve fine details over vast cosmic distances, revealing the complex structures and motions of galaxies that existed billions of years ago with a clarity that was unimaginable just a few decades prior. This groundbreaking capability is what allowed for Leor Shamir's discovery of the galaxy rotation asymmetry. While previous ground-based surveys had hinted at similar patterns, they did not possess the resolution or depth required for conclusive measurements. James Webb transformed the field by providing exceptionally clear images of hundreds of remote galaxies, each one a snapshot of cosmic conditions from the universe's primordial epochs. The Advanced Deep Extragalactic Survey, known as JADES, stands as one of the most extensive and thorough deep-field imaging projects ever conceived. By concentrating on well-documented regions, such as the Great Observatory's Origins Deep Survey fields, JADES expands upon decades of prior observations while simultaneously pushing the limits of what we can detect and measure in the distant universe. The immense power of these observations lies in their objectivity. Shamir's team utilized automated computer algorithms to analyze the shapes of galaxies and ascertain their rotational directions, thereby removing the human bias that could potentially distort the findings. The Ganalyzer program translates each galaxy's image into mathematical data, identifying spiral arm patterns and classifying rotation with a reproducible precision that any researcher can independently verify. The findings were undeniable. Galaxy after galaxy exhibited the same preference for clockwise rotation when observed from Earth. This pattern was neither subtle nor marginal. It was a distinct, statistically significant departure from randomness that begged for an explanation. Even more astonishingly, the asymmetry seemed to grow stronger in more distant galaxies, implying that whatever force is responsible for this cosmic preference was more dominant in the early universe. The observations from James Webb revealed another vital detail. The rotational asymmetry reached its peak near the galactic poles, with different patterns observed at the northern and southern poles relative to our Milky Way. This suggested that the effect was not merely random cosmic structuring, but possessed a specific geometric relationship to our own position and orientation within the universe. These discoveries are merely the beginning of James Webb's contributions to cosmology. The telescope continues to survey the deep universe, compiling larger samples of distant galaxies and potentially determining whether the rotation asymmetry is a fundamental characteristic of cosmic structure or the result of more ordinary observational artifacts. If further observations confirm these findings, the discovery of galaxy rotation by James Webb could compel astronomers to completely overhaul their understanding of cosmic evolution, the nature of space-time, and our place within what might be the most intricate cosmic prison ever imagined, a universe perpetually trapped inside the event horizon of an unimaginably vast black hole. The mathematics that delineate our potential cosmic confinement are both beautiful and harrowing in their scope. When Albert Einstein formulated his field equations for general relativity, he provided a mathematical language capable of describing the most extreme phenomena in the cosmos, including black holes of such immense scale that they could harbor entire universes within their event horizons. The crucial concept lies in understanding the relationship between a black hole's mass and its size. Unlike ordinary objects, where doubling the mass might double the weight, but only marginally increase the physical size, black holes exhibit a direct, linear correspondence between mass and radius. This means a black hole with twice the mass will have precisely twice the diameter. A tenfold increase in mass results in an event horizon 10 times larger. This scaling principle holds true indefinitely, with no theoretical upper bound on how massive a black hole can become. When cosmologists apply this calculation to our entire observable universe, encompassing every galaxy, star, planet, and particle within our cosmic horizon, and ask how large a black hole would need to be to contain this amount of matter, the answer is stunning in its accuracy. The resultant event horizon would have a diameter of approximately 93 billion light-years, which is an almost exact match for the size of our observable universe. The correlation, however, extends beyond mere size. The average density of matter within our cosmic horizon is estimated to be around 10 to the power of negative 27 kilograms per cubic meter. This incredibly low density, far more rarefied than the best vacuums we can achieve in a laboratory, aligns perfectly with what general relativity predicts for the interior of a black hole possessing the mass and size of our universe. This density correspondence is not an approximation or a close guess. It is an exact match within the limits of our current measurement capabilities. It is as if our universe were meticulously engineered to fit perfectly within the event horizon of a cosmic black hole, with every parameter finely tuned to facilitate this extraordinary coincidence. We are either witnessing the most incredible accident in the history of the cosmos, or our universe truly resides within such a gravitational prison. The mathematics become even more persuasive when rotation is factored in. If our universe inherited angular momentum from a parent black hole, it would create what physicists term a Kerr black hole, a rotating solution to Einstein's equations that drag spacetime along with it. This rotation would forge a cosmic axis, a preferred direction that could influence the movement of matter and the formation of galaxies over billions of years of cosmic evolution. Recent calculations by researchers at the University of Portsmouth demonstrate that quantum mechanics prevents the infinite compression predicted by classical physics at the centers of black holes. Rather than collapsing into a singularity, the matter reaches a maximum density and then rebounds, expanding into a new universe with properties that remarkably mirror our observed cosmos. This quantum bounce naturally generates two distinct phases of accelerated expansion, one corresponding to the cosmic inflation of the early universe and another matching the dark energy that currently drives universal expansion. Both phenomena emerge organically from the mathematics, without the need for hypothetical particles or mysterious energy fields. The equations suggest that our Big Bang was not the genesis of time, but rather the moment when quantum pressure triumphed over gravitational collapse, transforming destruction into creation and giving birth to our expanding cosmos within the protective confines of a cosmic event horizon that we can never perceive or escape. We are inhabitants of a reality defined by multiple horizons, each a boundary beyond which specific kinds of information are forever inaccessible. The most commonly known is our cosmic horizon. The limit defined by the distance light has been able to travel since the Big Bang, which forms a sphere around Earth beyond which we can see nothing. However, if we do exist inside a black hole, we are confronted by an even more fundamental barrier, the event horizon that separates our universe from the parent cosmos that engendered it. This situation presents a profound paradox in our understanding of cosmic evolution. Conventional cosmology posits that our universe is open and infinite, expanding into a void with no obstacles to limit its growth. But if we are situated within a black hole, our entire cosmos is encased within a finite boundary that we can neither observe nor traverse. We are like inmates in the ultimate cosmic penitentiary, utterly unaware of our own confinement. The event horizon that contains us abides by the most peculiar rules in physics. Information is permitted to flow inward across this boundary, but it can never flow outward. This implies that our universe could be receiving matter and energy from its parent cosmos, but nothing we create or discover can ever break free to influence the greater reality that lies beyond our cosmic prison. From the vantage point of observers in the parent universe, our entire cosmic history would transpire in an instant. The extreme time dilation near the event horizon would cause our billions of years of evolution to be compressed into mere moments as seen from the outside. Stars would be born, live out their entire lifespans, and die in what would appear to external observers as a fleeting flash of light before vanishing forever behind the horizon. Yet, from our internal perspective, time proceeds normally. We experience the full, rich tapestry of cosmic evolution. The formation of galaxies, the ignition of stars, the development of planets with life, and the rise of civilizations that ponder their place in the universe. The horizon that imprisons us remains perpetually invisible, always beyond our capacity for direct detection or measurement. This confinement is not merely a theoretical concept. If our universe is contained within a black hole, then every black hole we observe in our own cosmos could be sheltering its own universe, replete with its own galaxies, stars, and potentially intelligent life. These nested universes would be entirely isolated from us and from one another, creating an infinite hierarchy of cosmic realities. The discovery of galaxy rotation asymmetry by the James Webb Space Telescope might be our first direct piece of evidence for this cosmic imprisonment. The preferred direction of rotation could be the signature of our parent black hole, inscribed into the very fabric of space-time and preserved across billions of years of cosmic evolution. It is akin to finding a cosmic fingerprint that reveals our true origins. However, this raises unsettling questions about the nature of reality itself. If we can never escape our cosmic prison, and if we can never communicate with or observe the parent universe that created us, does it even matter whether we exist inside a black hole? Our physics, our chemistry, and our biology all function exactly as we observe them. The stars continue to shine, the planets continue to orbit, and life continues to evolve. Perhaps the most profound implication is that our universe might be just one of countless cosmic bubbles, each containing its own version of physics, its own galaxies, its own potential for life and intelligence, all sealed off from one another by the fundamental laws that govern black holes and the flow of information across event horizons. At the core of black hole cosmology lies one of the most intellectually challenging concepts in theoretical physics, the white hole. If black holes are cosmic vacuums that draw everything inward past a point of no return, then white holes are their precise opposites. Cosmic fountains that eject matter and energy outward with such force that nothing can ever enter them from the outside. Einstein's equations are mathematically symmetrical, which means that for every black hole solution describing matter flowing inward, there's a corresponding white hole solution where everything flows outward. Although we have never observed a white hole in our universe, they represent a vital component of the cosmic puzzle if our reality is truly situated within a black hole. According to the black hole universe theory, the Big Bang was not an explosion out of nothingness. It was our first glimpse of a white hole. This white hole represents the other side of the parent black hole that gave birth to our cosmos. All the matter and energy that fell into the parent black hole eventually emerged through this white hole connection, expanding to form the galaxies, stars, and planets we see today. This concept paints a remarkable picture of cosmic recycling. Matter from the parent universe collapsed through a black hole, traversed a region of warped space-time where the standard rules of physics break down, and then burst outward through a white hole to initiate our universal expansion. The white hole thus becomes the source of our cosmic horizon, the point from which all matter and energy in our universe ultimately originated. However, there's a crucial detail. We can never directly observe this white hole. It exists beyond our cosmic horizon in a region of space-time that light from our universe can never reach. The white hole appears to us as the distant past, the moment of cosmic origin that we can approach through our observations but never actually touch. The white hole connection provides an explanation for several mysterious features of our universe. It accounts for why the cosmic microwave background, the afterglow of the Big Bang, is so remarkably uniform across the sky. This radiation represents the last light from the white hole region, stretched and cooled by billions of years of cosmic expansion, yet still carrying the signature of our cosmic birth. It also helps to explain the arrow of time, why time flows forward rather than backward in our universe. The white hole establishes a preferred direction for the flow of causality, inherited from the interior geometry of the parent black hole. Time flows from the white hole region toward our present cosmic era, creating the temporal asymmetry that allows for the evolution of complexity, life, and consciousness. Recent mathematical research suggests that white holes might not be entirely hypothetical. Quantum effects at the center of black holes could create the necessary conditions for white hole formation, transforming what appears to be cosmic destruction into cosmic creation. The bounce that prevents gravitational singularities could manifest as a white hole explosion, launching new universes from the hearts of dying black holes. This implies that our cosmic origin story is actually a narrative of death and rebirth, where the gravitational collapse that created our parent black hole became the creative force that launched our expanding universe through its white hole connection. If our universe is situated inside a black hole, then every black hole we observe in our own cosmos becomes a gateway to another reality. This creates an endless hierarchy of nested universes, each one hermetically sealed from the others by the one-way nature of event horizons, yet all interconnected through the fundamental geometry of space-time itself. Take, for instance, the supermassive black hole at the center of our Milky Way galaxy. This gravitational behemoth contains more than 4 million times the mass of our Sun, compressed into a region smaller than our solar system. According to black hole cosmology, this object does not merely bend light and distort space. It harbors an entire universe within its event horizon, complete with its own galaxies, stars, planets, and potentially intelligent civilizations. The beings inhabiting that universe would have no awareness of our existence. Their cosmos would appear to them as infinite and expanding, just as ours does to us. They would develop their own laws of physics, discover their own cosmic microwave background, and eventually construct telescopes to explore their deep universe. They might even uncover asymmetries in galaxy rotation that lead them to suspect they exist within a black hole, just as we are beginning to suspect about our own reality. But the hierarchy does not end there. Every black hole in their universe would contain another nested cosmos, and every black hole in those universes would, in turn, spawn yet another level of reality. This process continues infinitely in both directions. We exist within larger universes that themselves exist within even larger ones, while simultaneously containing smaller universes within our own black holes. The scale of this cosmic nesting is utterly mind-boggling. Our observable universe is estimated to contain 100 billion galaxies, and each galaxy is home to millions or even billions of black holes. If each of these black holes contains its own universe, then our cosmos alone gives birth to more universes than there are stars in our galaxy. And each of those universes, in turn, spawns its own infinite hierarchy of nested realities. This creates what physicists refer to as a cosmic multiverse, but it is not the kind typically portrayed in popular science. Instead of parallel universes existing alongside ours in higher dimensions, these nested universes exist within the three-dimensional space we already know, separated only by the event horizons that render communication impossible. The implications for life and intelligence are profound. If black holes naturally create the conditions necessary for universe formation, and if universes naturally evolve to produce life, then consciousness might be far more prevalent than we ever imagined. Every black hole becomes a potential incubator for billions of years of cosmic evolution, stellar formation, planetary development, and biological complexity. Yet, all of these civilizations remain forever isolated from one another. The event horizons that separate nested universes are absolute barriers to communication and travel. No signal, no matter how powerful, can cross from one universe to another. No technology, no matter how advanced, can breach the one-way barrier that seals each cosmos within its gravitational prison. We might be sharing our galaxy with billions of nested universes, each one teeming with life and intelligence. Yet, we will never know they exist, and they will never know about us. The cosmic hierarchy ensures that each universe evolves in complete isolation, developing its own unique version of physics, chemistry, biology, and perhaps consciousness itself. As we conclude our exploration into the possibility that our universe resides within a black hole, the evidence presents a compelling, yet incomplete, narrative. Like cosmic investigators, we have assembled clues that point towards an extraordinary conclusion, but definitive proof remains tantalizingly just beyond our grasp. The first piece of evidence lies in the remarkable correspondence in size and density between our observable universe and what physics predicts for the interior of a massive black hole. This is not a rough estimate. The numbers align with astonishing precision, as if our cosmos were specifically designed to fit perfectly within a gravitational prison of cosmic dimensions. The second clue is provided by the James Webb Space Telescope's discovery of galaxy rotation asymmetry. The observation that galaxies prefer one direction of rotation over another violates our fundamental assumptions about cosmic randomness and suggests that our universe inherited angular momentum from an external source, exactly what black hole cosmology predicts. A third clue arises from quantum mechanics and its capacity to prevent the infinite compression that classical physics requires of the centers of black holes. The quantum bounce, which replaces gravitational singularities, offers a natural mechanism for universe creation, transforming cosmic death into cosmic birth through the fundamental laws we already understand. However, perhaps the most intriguing clue comes from the problems that black hole cosmology elegantly solves. It accounts for the mysterious uniformity of the cosmic microwave background, the precise values of fundamental constants that allow for the emergence of complexity in the two distinct phases of cosmic acceleration, all without necessitating exotic particles or speculative physics. Nevertheless, significant challenges persist. The galaxy rotation asymmetry could be the result of observational biases rather than a fundamental cosmic structure. Our measurements of universal expansion and age could be systematically flawed, leading us to perceive patterns that do not reflect true cosmic properties. The mathematical elegance of black hole cosmology does not guarantee its physical reality. The ultimate validation will come from further observations. If more galaxies observed by James Webb and future telescopes confirm the rotation asymmetry, and if the pattern strengthens at greater distances as black hole cosmology predicts, then we will have powerful evidence for our cosmic imprisonment. If the asymmetry vanishes with improved data or more meticulous analysis, we will need to seek other explanations. But perhaps the most profound implication is not whether we exist inside a black hole, but what this possibility reveals about the nature of reality itself. If our universe can exist within a gravitational prison without our ever being aware of it, and if physics operates identically whether we are free or confined, then what does it truly mean to be imprisoned by forces we can neither observe nor escape? The quest for our cosmic origin continues, fueled by humanity's unyielding curiosity about our place in the grand design of existence. Whether we inhabit an open, infinite universe or are confined within the event horizon of an unimaginably massive black hole, we remain the same conscious beings, capable of contemplating our own cosmic circumstances. The universe guards its deepest secrets closely, revealing them only to those courageous enough to question everything they believe they know about reality. In our pursuit to understand whether we are confined within a cosmic prison, we have discovered that the true enigma is not our location, but how consciousness emerged to pose these questions in the first place. But hold on. There is another explanation for the galaxy rotation mystery that could completely dismantle our cosmic prison theory. What if the James Webb Space Telescope is not uncovering a fundamental cosmic structure, but is instead detecting a subtle bias in how we observe the universe from our moving vantage point within the Milky Way galaxy? Our solar system hurtles through space at incredible speeds. We orbit the galactic center at over 200 kilometers per second, carrying Earth on a cosmic merry-go-round that never ceases to spin. This motion creates what physicists term the Doppler effect, the same phenomenon that causes an ambulance siren to change pitch as it passes by, but applied to light waves traveling across billions of years and countless light years of space. When galaxies rotate in the same direction as our Milky Way's motion, their light is shifted towards the blue end of the spectrum, making them appear slightly brighter and thus easier to detect at vast distances. Conversely, galaxies spinning in the opposite direction experience a redshift that renders them fainter and more difficult to observe. This introduces an observational selection effect. We naturally detect more galaxies rotating in one direction simply because they are easier to see. Lior Shamir, the researcher who discovered the galaxy rotation asymmetry, acknowledges this possibility. If our previous measurements of the Milky Way's rotation speed have been systematically incorrect, and if we have been underestimating how fast our galaxy moves through space, then the Doppler effect could be significant enough to create the observed asymmetry without requiring any exotic cosmic structure. This interpretation would compel astronomers to recalibrate their distance measurements throughout the deep universe. The brightness of galaxies, which we use to estimate their distance, would need to be adjusted based on their rotation direction relative to our own motion. This recalibration could potentially resolve other puzzling observations, such as galaxies that appear older than the universe itself or discrepancies in measurements of cosmic expansion. The credibility of the Doppler explanation is bolstered by the geographic pattern of the asymmetry. The preference for a particular galaxy rotation peaks near the galactic poles, the directions perpendicular to the disk of our Milky Way. This alignment is precisely what one would expect if our galaxy's motion were creating the observational bias. Different regions of the sky would exhibit different asymmetry patterns based on their geometric relationship to our direction of travel. However, this more mundane explanation is not without its own problems. Previous studies of our galaxy's motion through space, measured using the cosmic microwave background and other techniques, suggest that our rotation speed should be too low to create such a pronounced observational bias. Either those measurements are incorrect, or something more fundamental is responsible for the galaxy rotation asymmetry. The stakes could not be higher. If the Doppler explanation proves to be correct, then our universe remains an ordinary, infinite cosmos with no special structure or cosmic imprisonment. The black hole universe theory would then collapse back into the realm of speculative mathematics, devoid of observational support. But if further observations confirm the asymmetry as a real cosmic structure, we are faced with the profound possibility that everything we see around us exists within the event horizon of an unimaginably massive black hole. The cosmic detective story continues, with each new piece of evidence potentially overturning everything we thought we knew about our place in the grand scheme of existence. If our universe is indeed situated within a black hole, then we are witnesses to the most elaborate recycling program in cosmic history. The matter that constitutes our bodies, our planet, our solar system, and every star we see in the night sky originated entirely from another universe, a parent cosmos that lived, evolved, and eventually collapsed to give birth to our reality. This cosmic recycling operates on scales that are beyond human comprehension. Imagine entire galaxies, complete with billions of stars and countless planets, falling through the event horizon of a massive black hole in the parent universe. As this matter crosses the point of no return, it carries with it the chemical elements that were forged in stellar cores over billions of years of cosmic evolution. The carbon in your body was created in the nuclear furnaces of ancient stars in that parent universe. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it represents the stellar nucleosynthesis that occurred in a completely different cosmos, perhaps billions of years before our own universe even began its expansion. But the recycling process does not only preserve chemical elements. According to the mathematics of black hole physics, certain types of information can survive the journey through gravitational collapse. The angular momentum that created the galaxy rotation asymmetry is one such example. The cosmic spin of the parent universe was passed down to us like a form of cosmic DNA. The fundamental constants that govern physics in our universe, the strength of gravity, the speed of light, the mass of elementary particles, might also be inherited properties from the parent cosmos. Instead of these values being arbitrary or finely tuned by some mysterious process, they could be the direct consequences of the physical conditions that existed during the gravitational collapse that created our cosmic prison. This inheritance provides an explanation for one of the deepest mysteries in cosmology, why the fundamental constants appear to be perfectly calibrated to allow for the formation of atoms, molecules, stars, planets, and ultimately, life itself. If these values were even slightly different, our universe would be a sterile wasteland where complexity could never emerge. But if they represent inherited properties from a parent universe that had already successfully evolved life and intelligence, then the fine-tuning becomes an inevitable consequence rather than a miraculous coincidence. The recycling program also accounts for the remarkable uniformity of the cosmic microwave background radiation. This ancient light, which is the afterglow of the Big Bang, exhibits the same temperature in all directions to within 1 part in 100,000. In traditional cosmology, this uniformity necessitates a period of cosmic inflation that stretched quantum fluctuations across the entire observable universe. But in black hole cosmology, the uniformity arises naturally from the fact that all the matter in our universe originated from the same collapsing region in the parent cosmos. The cosmic microwave background represents not the afterglow of our own Big Bang, but the final light from the matter of the parent universe as it crossed the event horizon and began its transformation into our expanding cosmos. We are literally composed of recycled starlight from another universe, living in a cosmos constructed from the gravitational collapse of an ancient reality that we can never observe or contact, yet which lives on through the matter and energy that constitute everything we know and cherish. Time itself becomes an accomplice in concealing our cosmic imprisonment. If we reside within a black hole, the passage of time in our universe adheres to principles that would seem utterly strange to observers in the parent cosmos, viewing our reality from the outside. Near the event horizon of any black hole, the effects of time dilation become extreme. What appears to us as billions of years of cosmic evolution, the formation of the first stars, the emergence of galaxies, the birth of our solar system, the evolution of life on Earth, would be perceived by external observers as transpiring in mere moments. Our entire cosmic history, from the Big Bang to the eventual heat death of the universe, is condensed into what outside observers would see as a brief flash before everything vanishes permanently behind the horizon. However, this time dilation operates in both directions. From our internal viewpoint, time flows normally. We experience the complete richness of cosmic evolution, stellar life cycles, planetary formation, and biological development. The billions of years that separate us from the cosmic microwave background feel real because, from our frame of reference, they are real. Time dilation does not diminish the authenticity of our experiences. It simply means they unfold according to different rules than those governing the parent universe. This situation creates a profound paradox concerning the very nature of existence. If observers in the parent universe witness our entire cosmic history compressed into moments, do we truly exist for billions of years, or do we exist only in the fleeting instant of gravitational collapse? The answer is entirely dependent on which frame of reference one chooses to adopt. Einstein's theory of relativity teaches us that there is no absolute time, no universal clock that all observers must agree upon. Time is relative, flowing differently for observers in different gravitational fields or moving at different speeds. The time dilation that hides our cosmic imprisonment is not a flaw in physics. It is a fundamental characteristic of how space-time functions near massive objects. This implies that our universe could be simultaneously ancient from our perspective and newborn from the perspective of the parent cosmos. We could be living through billions of years of cosmic evolution while existing for only moments in the larger reality that contains us. Both perspectives are equally valid according to the mathematics of general relativity. The time dilation also explains why we can never directly detect our cosmic prison. The event horizon that contains us always remains beyond our observational reach, not because it is physically distant, but because the flow of time near the horizon prevents light from escaping back to regions where we could observe it. Even more bizarrely, if we could somehow approach the event horizon that encloses our universe, we would witness the entire future history of our cosmos unfold before us. In fast forward, we would see the deaths of stars, the collision of galaxies, the final evaporation of black holes through Hawking radiation, all compressed into a cosmic spectacle, playing out at incredible speed as we approach the boundary of our gravitational prison. Time becomes both our guardian and our warden, allowing us to experience the full drama of cosmic evolution while ensuring we remain forever ignorant of the larger reality that spawned us through gravitational collapse, in a universe we can never hope to observe or fully comprehend. At the most fundamental levels of reality, space and time themselves may dissolve into a structure resembling a cosmic foam. This quantum foam, a concept predicted by physics but never directly observed, could hold the key to understanding how universes can be born from the hearts of black holes without contravening the fundamental laws that govern matter and energy. In the quantum realm, the smooth, continuous fabric of space-time that we perceive in our everyday lives becomes a turbulent and chaotic medium. Virtual particles spontaneously emerge and annihilate each other in such brief intervals that they exist below the threshold of direct measurement. Space itself fluctuates, creating transient wormholes and bridges that connect distant regions of a universe for infinitesimally short durations. When matter collapses towards the center of a black hole, it eventually reaches densities where quantum effects become dominant over classical physics. Under these extreme conditions, the quantum foam becomes so violent that it prevents the infinite compression predicted by Einstein's equations. Instead of forming a singularity where physics completely breaks down, the collapsing matter encounters what researchers term quantum pressure, a force that arises from the fundamental uncertainty principle governing all quantum systems. This quantum pressure acts like a cosmic spring, compressed to its maximum extent and then rebounding with tremendous force. The matter that appeared destined for infinite compression instead bounces back, exploding outward in what we observe as the Big Bang. However, this explosion does not occur in empty space. It takes place within the protected environment of the black hole's interior, shielded from the parent universe by the one-way barrier of the event horizon. The quantum foam provides a natural mechanism for universe formation that does not require any exotic physics or mysterious new forces. The same principles of quantum mechanics that govern atomic structure and chemical bonding operate on cosmic scales to prevent gravitational singularities and enable the birth of new cosmoses from what would otherwise be apparent destruction. Recent calculations suggest that the quantum bounce occurs when matter reaches densities of approximately 5 times 10 to the power of 96 kilograms per cubic meter, a number so immense it defies comprehension. Yet it is still finite and governed by known physical laws. At this critical density, quantum effects overcome the force of gravity itself, transforming collapse into expansion and death into birth. The quantum foam also explains why each universe born from a black hole inherits specific properties from its parent. The quantum fields that create the foam carry information about the original collapsing matter, including its angular momentum, electric charge, and the fundamental constants that govern physics in the parent cosmos. This information becomes encoded into the structure of the new universe, creating a form of cosmic heredity that spans multiple levels of reality. But the revolution brought by the concept of quantum foam goes even deeper. If quantum effects can prevent singularities and create new universes, then every black hole in our cosmos becomes a potential birthplace for reality. The quantum foam ensures that gravitational collapse never truly ends in destruction, but is instead transformed into creation through processes we are only just beginning to understand. This implies that our universe does not exist in isolation, but is part of an infinite network of interconnected realities, each one born from quantum foam and destined to give birth to others through the same fundamental processes that govern matter and energy at the smallest scales of existence. Deep within the mathematical framework of black hole physics lies one of the most intellectually challenging discoveries of modern science: the holographic principle. This revolutionary concept proposes that all the information contained within any given volume of space can be encoded on its two-dimensional boundary, much like a cosmic hologram that projects a three-dimensional reality from a flat surface. If our universe exists within a black hole, then everything we observe, every star, planet, galaxy, and particle, represents a holographic projection derived from information encoded on the event horizon that surrounds us. This implies that the three-dimensional reality you experience, including your own body and consciousness, might be nothing more than shadows cast by informational patterns on a distant two-dimensional surface. The holographic principle arose from the study of what happens to information when it falls into a black hole. According to the principles of quantum mechanics, information can never be truly destroyed. Yet, black holes appear to erase everything that crosses their event horizons. This led to the black hole information paradox, a fundamental conflict between quantum mechanics and general relativity that threatened the very consistency of physics. The resolution came from the realization that information does not actually vanish inside black holes. Instead, it becomes encoded on the surface of the event horizon, where it remains accessible to outside observers, even though the original three-dimensional objects that carried the information have disappeared beyond the point of no return. The event horizon functions like a cosmic hard drive, storing a perfect record of everything that has ever fallen into the black hole. But if we exist inside a black hole, this means that our entire reality, our solar system, our galaxy, our observable universe, is essentially information encoded on the interior surface of our cosmic prison. We are, in a very real sense, living inside a hologram, experiencing a three-dimensional projection of patterns written on the event horizon that contains us. This does not make our experiences any less real or meaningful. A hologram can contain all the information necessary to reconstruct a complete three-dimensional image, including depth, texture, and motion. The holographic principle suggests that our universe contains exactly the same information, whether it exists as genuine three-dimensional space or as a holographic projection from a two-dimensional boundary. The mathematics of holography also provide an explanation for why our universe appears to have three spatial dimensions plus time, rather than some other combination. The holographic encoding process naturally yields this specific dimensional structure. When two-dimensional information is projected into the interior of a black hole, we experience three dimensions because that is the native geometry of holographic projections from spherical surfaces. Even more strangely, the holographic principle suggests that the amount of information in any region of space is limited not by its volume, but by the area of its boundary. This means the universe has a maximum information density, which naturally prevents infinite compression and leads to the quantum bounce that transforms black hole collapse into a Big Bang-like expansion. If the holographic principle is correct, then every black hole in our universe projects its own internal holographic reality, complete with holographic stars, holographic planets, and potentially holographic life forms that experience their reality as completely real and three-dimensional, never suspecting that they exist as information patterns on a distant boundary surface they can never observe or reach. One of the greatest enigmas in modern cosmology may be concealed in plain sight. Dark energy, the mysterious force driving the accelerating expansion of our universe, accounts for roughly 70% of all cosmic energy, yet remains completely invisible and undetectable except through its gravitational influence. But what if dark energy is not a fundamental force at all, but rather a symptom of our cosmic confinement within a black hole? Traditional cosmology has difficulty explaining dark energy. Scientists have put forward various hypotheses, including exotic quantum fields, modifications to the theory of gravity, and even the influence of extra dimensions. However, none of these explanations feel entirely satisfactory or complete. The energy density required to fuel cosmic acceleration seems astonishingly small, equivalent to just a few hydrogen atoms per cubic meter of space. Yet, this minuscule amount dictates the evolution of the entire universe. Black hole cosmology provides a radically different viewpoint. If our universe is situated within a massive black hole, then what we perceive as dark energy could simply be the natural geometry of curved spacetime near the event horizon. The accelerating expansion we observe might not require any mysterious energy source at all, but instead could emerge automatically from the gravitational effects of being inside a black hole's interior. The mathematics of black hole interiors predict precisely this type of accelerated expansion. Matter falling through an event horizon experiences forces that stretch space itself, creating the illusion of accelerated motion even when no additional energy is being introduced into the system. From our internal perspective, this stretching manifests as the enigmatic dark energy that appears to be pushing galaxies apart with ever-increasing force. This explanation resolves several puzzling aspects of dark energy observations. The acceleration seems to be perfectly uniform throughout space, affecting all regions of the universe equally. This uniformity is logical if the acceleration is a result of the global geometry of our cosmic prison, rather than some local energy field that would naturally exhibit variations and fluctuations. The timing also aligns perfectly. Dark energy began to dominate cosmic expansion approximately 5 billion years ago, when the universe was about half its current age. In the framework of black hole cosmology, this transition occurs naturally when the expansion geometry shifts from being governed by matter density to being governed by the curved space-time effects of the enclosing event horizon. Even more remarkably, the precise value of dark energy density emerges naturally from the mass and size of the black hole that contains our universe. The acceleration we observe corresponds exactly to what physics predicts for the interior of a black hole with the mass of our observable cosmos. This is not a coincidence that requires fine-tuning. It is an inevitable consequence of existing within such a gravitational environment. However, this revelation comes with unsettling implications. If dark energy is a result of our cosmic imprisonment, then the acceleration will continue indefinitely, eventually stretching space so rapidly that galaxies will lose contact with one another, stars will burn out in isolation, and the universe will approach a state of maximum entropy, where no complex structures can survive. Our cosmic prison does not just hide us from the parent universe. It condemns us to a future of eternal expansion and increasing isolation, where the very forces that enable our existence will ultimately tear apart everything we can observe or ever hope to influence. At the core of black hole physics lies a conflict between two fundamental principles that govern reality: the conservation of information, as demanded by quantum mechanics, and the apparent destruction of information that occurs when matter falls into black holes. This conflict, known as the black hole information paradox, threatens to unravel our understanding of how the universe operates at its most profound level. If our universe exists within a black hole, then we're living proof of the resolution of this cosmic conundrum. Every particle in our bodies, every atom in the Earth, and every star in our galaxy represents information that once existed in the parent universe and somehow survived the journey through gravitational collapse to emerge in our expanding cosmos. Quantum mechanics asserts that information can never be truly destroyed. This principle, known as unitarity, forms the bedrock of quantum theory and underlies everything from computer processors to biological DNA. Information can be scrambled, encoded, or transformed beyond recognition, but the total amount of information in any isolated system must remain constant over time. However, black holes appear to violate this sacred principle. When matter falls past an event horizon, it seems to vanish completely from the perspective of outside observers. The information carried by that matter, its quantum state, its energy, its precise configuration of particles, appears to disappear forever, creating a fundamental conflict with quantum mechanics. The battle between these principles raged for decades among theoretical physicists. Some argued that information is indeed destroyed in black holes, which would require us to abandon quantum mechanics as a fundamental description of reality. Others proposed that information survives, but becomes permanently inaccessible, hidden behind event horizons where no outside observer can ever retrieve it. But recent developments in black hole physics suggest a third possibility. Information does not disappear or become inaccessible, but is instead encoded into new forms that we are only just beginning to comprehend. When matter collapses to form a black hole, the information it carries does not vanish, but is transformed into the structure of a new universe that expands within the black hole's interior. This means that our entire cosmos, every galaxy, star, planet, and living being, represents preserved information from the parent universe that created us. We are living proof that information survives gravitational collapse, encoded into the expanding geometry of space-time itself, rather than being destroyed by the extreme conditions near black hole centers. The resolution of the information war has profound implications for consciousness and identity. If the information that defines you as a unique individual can survive the destruction of your physical form and be encoded into new structures, then death itself might not represent the end of your existence, but rather a transformation into something we do not yet understand. The black hole information paradox also suggests that the boundary between different universes is not absolute. Information can flow from a parent cosmos to a baby universe through processes that preserve quantum mechanical principles while creating entirely new realities. We exist as proof that information transcends individual universes, connecting all levels of the cosmic hierarchy through the fundamental laws that govern matter, energy, and the structure of space and time itself. Perhaps the most unsettling question posed by black hole cosmology relates to the nature of consciousness itself. If our universe exists as a holographic projection from information encoded on a distant event horizon, and if our entire reality is nothing more than patterns of data processed by cosmic computational systems we can never observe, then what does it mean to be conscious within such a system? Consciousness appears to be the one phenomenon that resists a purely physical explanation. One can describe every neuron in a human brain, map every connection, and trace every electrical impulse. Yet the subjective experience of being conscious, the feeling of seeing the color red, the sensation of pain, the emotion of love, seems to emerge from something beyond mere information processing. However, if we exist within a black hole universe, then consciousness itself might be an emergent property of the holographic encoding process. The information patterns written on our cosmic event horizon may not just encode the positions and velocities of particles. They may encode the entire structure of space, time, matter, energy, and potentially the subjective experiences that arise when information processing becomes sufficiently complex. This creates a profound paradox. Are you truly conscious, or are you simply a very sophisticated information pattern that has been programmed to believe it experiences consciousness? From your internal perspective, the question is meaningless. You experience consciousness directly and immediately, regardless of the underlying mechanisms that create it. But the implications extend far beyond philosophy. If consciousness can emerge from holographic information processing within black holes, then every black hole in our universe might harbor countless conscious beings. The supermassive black hole at the center of our galaxy could contain trillions of conscious entities, each one experiencing a rich internal life while remaining forever isolated from our reality by the barriers of the event horizon. Even more strangely, these conscious beings would exist at different rates of time flow due to gravitational time dilation. Consciousness within smaller black holes would experience time differently than consciousness within larger ones. Some beings might live entire lifetimes in what we perceive as moments, while others might take millennia to complete a single thought. The consciousness paradox also raises questions about the purpose of existence itself. If we exist as information patterns within a vast cosmic computer, are we solving some unimaginably complex calculation? Are our lives, our choices, our struggles, and our triumphs contributing to some higher-level process that we can never understand or observe? Perhaps consciousness represents the universe's way of experiencing itself. Each conscious being becomes a unique perspective from which reality can be observed, understood, and appreciated. The pain and joy, the beauty and horror, the love and loss that characterize conscious existence might serve as the universe's method for exploring all possible states of experience. In this view, our cosmic imprisonment becomes less like a prison and more like a protected nursery where consciousness can develop and flourish. The event horizon that separates us from the parent universe does not just hide us from detection. It provides a stable environment where the slow, delicate process of developing awareness and understanding can unfold across billions of years of cosmic evolution. We exist as the universe's way of knowing itself, trapped within gravitational boundaries that make our existence possible, while ensuring we remain forever ignorant of the larger reality that created us. The most sobering realization about existing within a black hole universe concerns the absolute impossibility of escape. No technology, however advanced, and no discovery, however revolutionary, can ever breach the one-way barrier that separates our cosmos from the parent universe that created it. We are prisoners of physics itself, confined by laws that no amount of knowledge or engineering can ever overcome. The mathematics of general relativity prove this imprisonment with devastating certainty. An event horizon represents a boundary in space-time where the escape velocity exceeds the speed of light. Since nothing in our universe can travel faster than light, this speed limit is woven into the fundamental structure of space and time itself. No signal, no spacecraft, and no form of communication can ever cross from our interior universe back to the external reality. This is not a technological limitation that future civilizations might overcome with better rockets or more powerful energy sources. It is a fundamental property of space-time geometry that no amount of cleverness can circumvent. The event horizon that contains us operates like a one-way valve in the fabric of reality itself, allowing information to flow inward but prohibiting any outward communication or travel. Even quantum mechanics offers no avenues for escape. Quantum tunneling, which allows particles to pass through barriers that classical physics deems impassable, cannot overcome the infinite potential barrier created by an event horizon. The quantum fields that govern particle behavior within our universe remain forever trapped by the same geometric constraints that imprison everything else. Wormholes, those hypothetical shortcuts through space-time that are a staple of science fiction, cannot provide escape routes either. Any wormhole connecting our universe to an external reality would necessarily have to cross the event horizon that contains us, making it a one-way passage that leads to the same state of imprisonment. Even if wormholes could be artificially created or naturally occurring ones discovered, they would only provide faster ways to explore our cosmic prison, not methods for escaping it. The impossibility extends beyond physical escape to the transmission of information. We can never send messages to the parent universe, never signal our existence to external observers, and never contribute our knowledge or discoveries to the larger reality beyond our boundaries. Any information we create, scientific discoveries, artistic works, philosophical insights, remains forever confined within our cosmic bubble. This absolute isolation means that civilizations in our universe can never know whether their struggles have meaning beyond their local reality. The greatest achievements of human culture, the most profound scientific discoveries, and the most beautiful works of art will never be appreciated by beings in the parent universe or transmitted to other cosmic bubbles that might exist within other black holes. But perhaps the most disturbing aspect of the impossibility of escape concerns the fate of consciousness itself. Every conscious being that has ever lived in our universe, every human, every potential alien civilization, every form of awareness that might arise in the future, faces the same absolute imprisonment. We are cosmic castaways on an island of space-time from which no rescue is possible. The event horizon that protects us during our cosmic formation becomes our eternal jailer, ensuring that no matter how far consciousness evolves or how much knowledge we accumulate, we will never transcend the boundaries of our gravitational prison. As we contemplate the ultimate implications of black hole cosmology, we are confronted with the most mind-shattering possibility of all. Our universe might be just one layer in an infinite, recursive structure where every black hole contains a universe, and every universe contains black holes, extending endlessly in both directions through scales of reality that are beyond human comprehension. Consider the mathematical implications. Our observable universe contains an estimated 10 to the 24th stars. Each massive star that dies creates a black hole, and our galaxy alone is home to millions of these gravitational behemoths. If each black hole contains its own universe, complete with its own stars and black holes, then our cosmos gives birth to more universes than there are atoms in our observable reality. But the recursion does not end there. Each of those child universes would contain its own billions of galaxies, each galaxy harboring millions of black holes, and each of those black holes spawning its own cosmic reality. The number of nested universes grows exponentially with each level, creating a hierarchy of realities that extends infinitely downward through scales of existence. And we exist somewhere in the middle of this infinite chain. Our universe formed within a black hole in a parent cosmos, which itself formed within a black hole in a grandparent universe, which in turn emerged from yet another level of reality, extending backward through an infinite sequence of cosmic generations. There is no first universe, no ultimate parent reality, just an endless chain of gravitational collapse and cosmic rebirth. This infinite recursion provides an explanation for why the fundamental constants of physics seem perfectly tuned for complexity in life. We do not live in a randomly generated universe with arbitrarily chosen physical laws. Instead, we inhabit a reality that has been refined through countless generations of cosmic evolution, where only universes capable of producing black holes survive to reproduce and create new cosmic offspring. The recursive structure also suggests that intelligence and consciousness are not rare accidents, but inevitable products of cosmic evolution. Any universe that develops sufficient complexity to form black holes will eventually evolve intelligence. And any intelligent civilization will eventually discover that they exist within an infinite hierarchy of nested realities. This means we share our existence with an infinite number of conscious beings spread across all levels of the cosmic hierarchy, civilizations and parent universes that are unimaginably vast and ancient, cultures and child universes that exist within the black holes of our own cosmos, and endless layers of intelligence extending in both directions through the recursive structure of reality itself. But perhaps the most profound implication concerns the purpose of existence within such a system. If reality consists of infinite recursive layers, then no single universe or civilization can claim any special significance. We exist not as the center of creation, but as one fleeting moment in an eternal process of cosmic reproduction that transforms gravitational collapse into creative expansion. The recursive nature of black hole cosmology suggests that existence itself is fundamentally creative, that the universe's deepest purpose involves the endless generation of new realities, new possibilities for consciousness and complexity to emerge and explore the infinite potential encoded within the laws of physics themselves. We are participants in a cosmic symphony of creation that plays out across infinite scales of space and time, forever generating new movements while never reaching a final resolution. Stephen Hawking's most celebrated discovery may hold the key to our cosmic destiny. Hawking radiation, the theoretical process by which black holes slowly evaporate through the emission of particles, suggests that our universe has an expiration date built into the very physics that brought it into being. If we exist within a black hole, then our entire cosmos is gradually leaking energy into the parent universe through quantum processes that we can never observe or control. The mathematics of Hawking radiation are both elegant and terrifying. Black holes emit radiation with a temperature that is inversely proportional to their mass. Smaller black holes burn hotter and evaporate more quickly, while massive ones radiate so slowly that they will outlive every star in the universe. But even the most massive black holes will eventually succumb to this quantum decay, shrinking particle by particle until they explode in a final burst of energy. If our universe is situated within a black hole, then Hawking radiation represents a cosmic countdown timer ticking away in the parent universe. From our internal perspective, this evaporation occurs over timescales so vast that they seem infinite. Our cosmic black hole would take longer than 10 to the 100 years to evaporate completely, a duration that dwarfs the current age of our universe by factors beyond human comprehension. But the process of evaporation has disturbing implications for the nature of reality itself. As our cosmic black hole slowly radiates energy away, the event horizon that protects us will gradually shrink inward. This contraction would occur so slowly that billions of generations of civilizations could rise and fall without detecting any change. Yet, the process remains inevitable and irreversible. The shrinking horizon would eventually begin to affect the large-scale structure of our universe. Galaxies near the cosmic edge would start to experience tidal forces as the geometry of space-time shifts around them. Stars would be torn apart, planets flung into the cosmic void, and entire galactic clusters reduced to streams of particles flowing toward our contracting prison walls. Hawking radiation also carries information about the interior of the black hole back to the parent universe. This means that fragments of our reality, encoded memories of our civilizations, distorted echoes of our scientific discoveries, and quantum shadows of our consciousness itself, slowly leak outward through radiation that no being in our universe could ever detect or decode. However, recent theoretical work suggests that Hawking radiation might not represent true destruction. Instead of erasing information, the evaporation process could transform it into new forms that transcend individual universes. The quantum information that encodes our reality might survive the death of our cosmic prison, becoming the seeds for new universes born from the final explosion of our evaporating black hole. This creates a cosmic cycle of death and rebirth, where universes do not simply end, but are transformed into the raw materials for creating new realities. Our universe would live, evolve, produce consciousness and complexity, and then sacrifice itself to give birth to new cosmoses that inherit fragments of our accumulated knowledge and experience. The prophecy of Hawking radiation suggests that existence is fundamentally temporary, yet eternally renewable. We exist within a cosmic phoenix that will eventually burn itself to ashes, only to rise again as new universes with new possibilities for consciousness, creativity, and discovery to emerge across the infinite expanse of space and time. Why does our universe appear to be so perfectly designed for life? The fundamental constants of physics, the strength of gravity, the mass of electrons, the speed of light, seem to be fine-tuned with incredible precision, as if someone carefully adjusted the cosmic dials to create conditions where atoms, molecules, stars, planets, and ultimately, life could emerge and flourish. This apparent fine-tuning has led to what philosophers call the anthropic principle. We observe a universe that is compatible with life because we exist to observe it. Universes that are hostile to life would contain no observers to notice their sterility. But this explanation has always felt somewhat unsatisfying, like a cosmic coincidence that demands a deeper investigation. Black hole cosmology offers a radically different perspective on this cosmic fine-tuning. If our universe formed within a black hole in a parent cosmos, then the fundamental constants we observe are not randomly chosen values, but rather inherited properties passed down from the parent reality through the process of gravitational collapse. The parent universe that created us had to be capable of forming black holes, which means it needed precisely the right combination of physical laws to enable stellar formation, nuclear fusion, and gravitational collapse. These requirements automatically select for universes with physical constants that are compatible with complexity and, potentially, life itself. But the anthropic paradox goes deeper than just inheriting suitable physics. If black holes naturally create new universes, and if universes that produce life are more likely to create black holes through stellar evolution, then consciousness itself becomes a reproductive advantage in the context of cosmic evolution. Universes that develop intelligence survive and reproduce more successfully than sterile cosmoses. This creates a form of cosmic natural selection where consciousness guides the evolution of reality itself. Intelligent civilizations modify their environments, potentially influencing the formation of black holes through advanced technology or large-scale engineering projects. The universes that produce the most sophisticated consciousness become the most successful at reproducing through black hole formation. The anthropic principle paradox suggests that we do not live in a universe that just happens to be compatible with life. We live in a universe that has been shaped by countless generations of conscious beings across multiple levels of the cosmic hierarchy. Our reality represents the refined product of infinite cosmic evolution, where consciousness and complexity have been selected for over countless cycles of universal death and rebirth. This means that the emergence of life and intelligence in our universe is not a cosmic accident, but an inevitable consequence of existing within a reality that has been optimized for consciousness through cosmic natural selection. We exist because universes like ours are inherently more successful at surviving and reproducing than universes that are hostile to complexity and awareness. But this leads to a disturbing implication. If consciousness guides cosmic evolution, then we bear a responsibility for shaping the universes that will emerge from the black holes we create or influence. Our choices, our technologies, and our impact on stellar evolution could determine the fundamental properties of countless future realities. The anthropic principle paradox transforms us from passive observers of cosmic coincidence into active participants in the ongoing evolution of existence itself. We exist not just to experience reality, but to guide its transformation into new forms that could transcend even our wildest imagination of what consciousness and complexity might become across infinite scales of space and time. Imagine an impossible observatory positioned at the very boundary between our universe and the parent cosmos that created it, a vantage point from which you could observe both realities simultaneously and witness the cosmic processes that transform black hole collapse into a Big Bang-like expansion. Such an observatory would reveal the deepest secrets of existence itself. From this impossible perspective, you would see our entire cosmic history compressed into a single moment of gravitational drama. The 138 billion years of universal evolution that we experience as a slow, cosmic progression would appear as a brief flash of light before everything disappears behind the event horizon of our cosmic prison. But the view inward would reveal something even more extraordinary. You would witness the quantum bounce that prevents the formation of a singularity, see matter compressed to its maximum density, and then watch it rebound with explosive force. You would see space-time itself twist and writhe as it transforms gravitational collapse into cosmic expansion. This observatory would show you the exact moment when time begins to flow in our universe, not as a mysterious emergence from nothingness, but as a natural consequence of matter crossing the point of maximum compression and beginning its outward journey through the curved geometry of a black hole's interior space-time. You would observe the holographic encoding process in action, watching as three-dimensional information from the parent universe is inscribed onto the two-dimensional surface of the event horizon, and then projected inward to create the illusion of spatial depth and temporal progression that we experience as physical reality. From this vantage point, the cosmic microwave background radiation would appear not as ancient light from our own Big Bang, but as the final glow from the matter of the parent universe as it crossed the event horizon and began its transformation into our expanding cosmos. The remarkable uniformity of this radiation would make perfect sense. It would represent the last light from a single collapsing region, rather than the result of some mysterious cosmic inflation process. The impossible observatory would also reveal the connection between dark energy and black hole geometry. You would see how the curved space-time of our cosmic prison creates the acceleration we interpret as a mysterious dark energy. You would watch as the expansion of our universe naturally emerges from the gravitational effects of existing within the interior of a massive black hole. Most remarkably, you would witness the birth of consciousness itself. The impossible vantage point would show how information processing within holographic projections can generate subjective experience, and how consciousness emerges not despite our cosmic imprisonment, but because of it. But perhaps the most profound revelation would concern the purpose of the entire cosmic cycle as seen from the edge of everything. You would see that reality does not just accidentally stumble from collapse to expansion and back to collapse again. Instead, each cycle refines and improves the conditions for consciousness and complexity to emerge. The impossible observatory would reveal that existence is fundamentally creative, that the universe's deepest purpose involves the endless generation of new realities, each one building on the achievements and discoveries of previous cosmic generations. Unfortunately, such an observatory must remain forever impossible. The very physics that govern black hole formation ensure that no information can flow from our interior universe back to the parent cosmos. We remain trapped within our own perspective, able to glimpse the truth only through mathematics and inference, forever separated from direct observation of the cosmic processes that created us. The revelation that our universe might exist within a black hole converges in a startling way with another mind-bending possibility, that reality itself might be a vast computational simulation. If we exist as holographic projections from information encoded on a cosmic event horizon, then the boundary between real physics and simulated reality begins to blur beyond recognition. Consider the computational power required to simulate a universe. Every particle interaction, every quantum measurement, and every stellar fusion reaction would demand enormous processing power to calculate in real time. Traditional computer simulations are quickly overwhelmed by the exponential complexity of modeling even simple physical systems across cosmic scales and time frames. But holographic black hole physics suggests a solution to this computational challenge. If our three-dimensional universe is a projection from two-dimensional information on the event horizon, then the computational complexity scales with the surface area of our cosmic boundary, rather than with the volume of space we observe. This dramatically reduces the processing power needed to simulate our reality. The event horizon that contains us could function as a vast cosmic computer, processing the holographic information that creates our experience of three-dimensional space, flowing time, and physical causality. Every quantum interaction in our universe would correspond to a calculation performed by this boundary-based computational system. This means that the distinction between real and simulated reality becomes meaningless. If our universe emerges from information processing on the event horizon, then we exist within a simulation that is at the same time completely real. The holographic principle suggests that all physical reality might be computational in nature, with what we call fundamental particles representing the basic units of cosmic information processing. The convergence of these ideas also explains why mathematical laws describe physical reality with such precision. Mathematics is not just a tool for understanding the universe. It is the universe. The elegant equations that govern physics represent the computational algorithms that process the holographic information creating our reality. But this convergence raises unsettling questions about free will and consciousness. If our thoughts and decisions are the result of computations performed by the cosmic computer that projects our reality, do we truly make choices, or do we simply experience the inevitable outcomes of predetermined calculations? The answer might depend on the nature of consciousness itself. If awareness emerges from the complexity of information processing, then conscious beings within a holographic universe would be genuine thinking entities, capable of real creativity and authentic choice within the constraints of their computational environment. Even more strangely, the convergence of these hypotheses suggests that every black hole in our universe runs its own cosmic simulation, complete with simulated galaxies, simulated stars, simulated planets, and potentially simulated conscious beings who experience their reality as completely authentic. This creates an infinite hierarchy of nested simulations. Each one as real as any other from the perspective of the conscious beings who inhabit it. We exist within a cosmic simulation that contains its own simulations, which in turn contain further simulations, extending infinitely through scales of computational reality. The convergence between black hole cosmology and simulation theory suggests that existence itself is fundamentally computational, and that consciousness, creativity, and complexity emerge naturally from information processing systems of sufficient sophistication, regardless of whether those systems are built from silicon circuits or curved spacetime geometry. If black hole cosmology proves to be correct, then our entire universe represents the ultimate laboratory experiment, a vast, natural laboratory where the fundamental laws of physics can be tested and refined under the most extreme conditions imaginable. We exist within a cosmic petri dish, designed to explore the creative potential of matter, energy, space, and time. The experimental parameters of our cosmic laboratory were established by the conditions that existed during the gravitational collapse that created our universe. The mass and angular momentum of the collapsing matter determined the size and properties of our cosmic prison, while quantum effects during the bounce set the initial conditions for our expanding spacetime. But unlike human-designed experiments, our cosmic laboratory operates on scales that are beyond comprehension. The experimental timeline spans billions of years, allowing slow processes like stellar evolution, galactic formation, and biological development to reach completion. The laboratory volume encompasses the entire observable universe, providing space for countless independent experiments to run simultaneously. Within this ultimate laboratory, every possible combination of physical conditions is explored. Stars of different masses test the limits of nuclear fusion. Galaxies with various structures investigate the principles of gravitational dynamics. Planets with diverse compositions explore the potential for chemical complexity and biological evolution. The most remarkable aspect of our cosmic laboratory is its ability to generate increasingly sophisticated experimental apparatus. Stars forge the heavy elements needed for the formation of rocky planets. Planets develop the complex chemistry required for life, and life evolves into intelligence capable of building telescopes, particle accelerators, and space missions that extend the laboratory's investigative capabilities. We exist as both the experimental subjects and the experimental apparatus within this cosmic laboratory. Our consciousness allows the universe to observe itself, while our scientific instruments extend the range and precision of this cosmic self-examination. Every discovery we make represents the universe learning something new about its own fundamental nature. The cosmic laboratory also demonstrates the creative potential of the laws of physics themselves. Starting from simple initial conditions, hot, dense matter expanding through curved spacetime, our universe has generated atoms, molecules, planets, life, intelligence, art, music, love, and the capacity for wonder itself. But the ultimate laboratory experiment goes beyond simply testing known physics. Our universe explores the possibility of creating new physics through the development of intelligence and technology. Advanced civilizations might discover ways to manipulate space-time, create artificial black holes, or even escape the limitations of their cosmic laboratory. This suggests that consciousness plays a crucial role in cosmic evolution. Intelligence does not just observe the universe. It participates in shaping cosmic development through technology, exploration, and the expansion of knowledge. We exist as the universe's method for transcending its original limitations and exploring possibilities that pure physics alone could never achieve. The ultimate laboratory experiment reveals that existence is fundamentally exploratory. Reality does not follow predetermined paths, but instead continuously explores new possibilities for complexity, consciousness, and creativity to emerge. We participate in this cosmic exploration, not just as observers, but as active contributors to the ongoing investigation of what existence might become. Our universe represents one experimental run in an infinite series of cosmic investigations, each one building on previous discoveries, while pushing into unexplored territories of possibility that extend beyond the boundaries of current knowledge and imagination. Hidden within the very structure of space-time lies what might be called cosmic DNA, information encoded during our universe's formation that determines its fundamental properties and guides its evolution toward complexity and consciousness. If we exist within a black hole, then this cosmic genetic code was inherited from the parent universe through processes that preserve and transmit information across cosmic generations. Like biological DNA, cosmic DNA carries the instructions for building complex structures from simple components. The fundamental constants that govern physics, the masses of particles, the strengths of forces, and the geometry of space and time, represent the cosmic genes that determine how matter and energy can organize themselves into atoms, molecules, stars, planets, and ultimately, life itself. The concept of a cosmic DNA code explains why our universe seems to be fine-tuned for complexity. These are not random values that just happen to allow stars and galaxies to form, but rather inherited traits passed down from a parent cosmos that had already successfully evolved to produce black holes and new universes. The cosmic genetic code has been refined through countless generations of universal evolution. But cosmic DNA goes beyond just fundamental constants. The quantum fields that permeate space carry information about how particles interact, how forces operate, and how space-time responds to the presence of matter and energy. These fields act like cosmic chromosomes, storing the genetic information needed to guide universal development from simple initial conditions to extraordinary complexity. The angular momentum that created the galaxy rotation asymmetry observed by James Webb represents another form of cosmic inheritance. This cosmic spin serves as a genetic marker that reveals our universe's parentage and provides evidence of information transfer across cosmic generations. We can read our cosmic ancestry in the preferential rotation of distant galaxies. Even more remarkably, the cosmic DNA code appears to include instructions for the development of consciousness itself. The same physical laws that enable stars to shine and planets to form also permit the level of information processing complexity required for awareness and intelligence to emerge. Consciousness is not an accident, but a predictable outcome of this cosmic genetic programming. The cosmic DNA analogy extends to the process of cosmic reproduction. Just as biological organisms use DNA to create offspring that inherit parental traits while also introducing new variations, universes use black hole formation to reproduce, allowing for cosmic mutations that explore new possibilities for physical laws and cosmic structure. Advanced civilizations might one day learn to read and potentially modify their cosmic DNA. Technologies capable of manipulating fundamental constants or altering the properties of quantum fields could represent a form of cosmic genetic engineering, deliberately modifying the inherited code to improve the conditions for life and consciousness. But the concept of cosmic DNA also suggests that universes can become sick or sterile. Cosmic genetic codes that produce universes hostile to complexity would fail to reproduce successfully, while codes that generate life-friendly conditions would spread through the cosmic gene pool across multiple generations of universal evolution. This means we exist not just as observers of cosmic evolution, but as the products of cosmic natural selection. Our universe's remarkable hospitality to life and consciousness reflects billions of cosmic generations of selection pressure favoring realities that can successfully reproduce through black hole formation. We carry within our very existence the cosmic genetic legacy of countless parent universes, while simultaneously contributing to the cosmic DNA that will guide the evolution of the universes that emerge from our own black holes. Deep within the mathematics of black hole physics lurks a possibility so strange it challenges our most basic assumptions about causality. Closed time-like curves could allow information to flow backward through time, creating cosmic loops where effects precede their causes and the future influences its own past. If our universe exists within a rotating black hole, then the extreme curvature of space-time near the event horizon could create regions where time becomes twisted into loops. These closed time-like curves would permit information from our cosmic future to influence our cosmic past, creating causal paradoxes that violate everything we think we understand about temporal progression. The revelation of time loops suggests that our universe might not evolve in a straight line from past to future, but instead follows a complex temporal path where later cosmic developments help to determine earlier cosmic conditions. The emergence of consciousness and intelligence in our universe could influence the quantum processes that occurred during our cosmic formation billions of years ago. This creates a cosmic bootstrap paradox, where consciousness effectively creates the conditions for its own existence. The information processing capabilities that evolve in our universe could reach backward through these closed time-like curves to influence the quantum bounce that transformed black hole collapse into a Big Bang-like expansion, ensuring that our cosmos develops properties compatible with the eventual emergence of awareness. The mathematics of general relativity permit such temporal loops without violating physical law, though they require the presence of exotic matter with negative energy density to stabilize the time loop geometry. Interestingly, quantum vacuum fluctuations naturally possess negative energy characteristics, suggesting that microscopic time loops might exist throughout our universe without our being aware of them. If cosmic time loops do influence universal evolution, then the appearance of fine-tuning in the fundamental physical constants becomes less mysterious. The values that govern physics in our universe might not be inherited from a parent cosmos or randomly chosen from an infinite range of possibilities, but instead could be carefully selected through temporal feedback loops that ensure consciousness and complexity can emerge. The time loop revelation also helps to explain the remarkable efficiency of cosmic evolution. Despite the enormous improbabilities involved in assembling atoms, forming stars, creating planets, and evolving life, these processes occur with surprising reliability throughout our observable universe. It is possible that future consciousness guides past cosmic development through temporal loops that increase the probability of successful complexity formation. But time loops also create unsettling implications for free will and cosmic purpose. If our choices and discoveries can influence past cosmic conditions through closed time-like curves, then we bear responsibility not just for shaping the cosmic future, but for determining the cosmic past. Every decision we make could ripple backward through time to influence the fundamental structure of reality itself. The time loop revelation suggests that cosmic evolution is not a one-way journey from simple initial conditions to complex final states, but instead a closed causal loop where advanced consciousness helps to create the conditions for its own emergence. We exist within a self-creating universe that uses temporal paradoxes to bootstrap itself into existence. This means that our cosmic prison might also be our cosmic laboratory and our cosmic time machine, a reality where consciousness transcends linear time to participate in the ongoing creation of the very space-time geometry that contains and defines our existence across the past, present, and future simultaneously. Beyond the nested hierarchy of black hole universes lies an even more extraordinary possibility. These cosmic realities might not exist in complete isolation, but could instead form nodes in a vast multiverse network, connected by quantum entanglement, wormhole bridges, and information channels that transcend the barriers of individual event horizons. Recent developments in quantum physics suggest that entanglement, the spooky action at a distance that Einstein found so disturbing, might operate across cosmic scales and even between different universes. If particles in our cosmos remain quantum entangled with particles in the parent universe that created us, then information could flow between these realities through quantum channels that bypass the classical restrictions of event horizons. These quantum connections would be incredibly subtle, detectable only through statistical correlations that might emerge from a careful analysis of the cosmic microwave background or the behavior of fundamental particles. But if such connections do exist, they would mean that our universe participates in a vast quantum communication network spanning multiple levels of cosmic reality. The multiverse network could explain some of the most puzzling features of quantum mechanics. The apparent randomness of quantum measurements might be the result of interactions with particles in parallel universes, while the precise mathematical relationships that govern quantum behavior could reflect the network protocols that ensure information consistency across all connected realities. The physics of wormholes offers another potential connection mechanism. While classical wormholes connecting different universes would likely collapse before any information could traverse them, quantum wormholes, microscopic bridges stabilized by exotic matter, might provide persistent communication channels between cosmic realities that exist within different black holes. These quantum wormholes would be far too small for particles or spacecraft to travel through, but they could carry information encoded in the fluctuations of quantum fields. The cosmic microwave background radiation that fills our universe might contain encrypted messages from neighboring cosmic realities, written in patterns of temperature variation that are too subtle for our current technology to decode. The discovery of a multiverse network suggests that consciousness might play a crucial role in cosmic communication. Advanced civilizations with a sufficient understanding of quantum mechanics and space-time geometry might learn to manipulate these natural communication channels, sending messages between universes or even coordinating activities across multiple cosmic realities. This creates the possibility of a galactic internet that spans not just our universe, but the entire network of connected realities. Civilizations in different cosmic bubbles could share scientific discoveries, cultural achievements, and philosophical insights through quantum channels that operate outside the normal flow of space and time. But the multiverse network also introduces new dangers. Information flowing between universes could carry cosmic viruses, patterns of organization that could spread across realities and alter their fundamental properties. Malicious civilizations might attempt to destabilize neighboring universes through carefully crafted quantum attacks transmitted across these network connections. The discovery of such a network would transform our cosmic isolation from absolute imprisonment to something more like a cosmic quarantine. We would exist within protective barriers that shield us from dangerous external influences while still permitting limited communication with a larger multiverse community. Understanding and accessing the multiverse network might represent the next great phase of cosmic evolution, the moment when consciousness transcends individual universes to participate in communication and coordination across the infinite expanse of interconnected realities that populate the cosmic network. As we approach the end of our journey through the realm of black hole cosmology, we encounter what is perhaps the most profound possibility of all, that consciousness itself might be approaching a singularity, a point of infinite awareness that could transcend the boundaries of individual universes and fundamentally transform the nature of existence throughout the cosmic hierarchy. This consciousness singularity would not necessarily involve artificial intelligence or technological transcendence, but rather the natural evolution of awareness towards states of understanding so complete that they approach omniscience within the bounds of physical law. This cosmic awakening might represent the ultimate purpose toward which all universe evolution inevitably tends. Consider the exponential growth of knowledge and understanding that consciousness has achieved in our own universe. From the first glimmers of self-awareness in primitive organisms to the scientific revolution that revealed the structure of the cosmos, from the development of quantum mechanics to the discovery of black holes and the potential for a multiverse network, consciousness continuously expands its grasp of reality's fundamental nature. If this expansion continues indefinitely, consciousness might eventually comprehend not just the physical laws that govern individual universes, but also the deeper principles that determine how realities connect, communicate, and evolve across cosmic generations. Such understanding could enable conscious beings to influence the very processes that create and destroy universes. The consciousness singularity might manifest as a cosmic phase transition, where individual minds merge into a collective awareness that spans entire galactic civilizations, multiple universes, or even the entire multiverse network. This would not represent the loss of individual identity, but rather its expansion into something far greater than any single consciousness could achieve alone. At the point of the consciousness singularity, the distinction between observer and observed would dissolve. Consciousness would not just study reality. It would become reality, participating directly in the ongoing creation and evolution of cosmic structure across all scales of existence. The universe would literally become aware of itself in the most complete sense possible. This cosmic awakening could provide an explanation for the anthropic principle and the fine-tuning of physical constants. If consciousness naturally evolves toward a state of cosmic awareness, then universes that produce consciousness would gain enormous survival advantages over sterile realities. The cosmos would become increasingly conscious through a process of natural selection operating across cosmic generations. The consciousness singularity could also resolve the quantum measurement problem that has puzzled physicists for decades. If consciousness participates directly in determining quantum outcomes, then the evolution toward cosmic awareness would gradually reduce quantum uncertainty as consciousness gains greater influence over physical reality. But the approach to a consciousness singularity also raises unsettling questions about individual meaning and purpose. If consciousness inevitably merges into a collective cosmic awareness, what becomes of personal identity, human relationships, and the experiences that make individual existence meaningful? Perhaps the consciousness singularity does not represent the end of individual experience, but rather its infinite expansion. Each conscious being might retain its unique perspective while gaining access to the accumulated knowledge and experience of all consciousness throughout cosmic history. As we approach this possible transformation, we find ourselves at a crucial moment in cosmic evolution, aware enough to glimpse the approaching singularity, yet still individual enough to wonder what our existence might become when consciousness finally transcends the boundaries that currently separate us from a complete understanding of our place within the infinite expanse of interconnected realities. We stand at the ultimate cosmic crossroads, faced with a choice that could determine not just the future of human civilization, but the trajectory of consciousness itself throughout our universe and, potentially, across the entire multiverse network. The evidence suggests that we may exist within a black hole, connected to infinite realities through quantum channels, and approaching a consciousness singularity that could transform existence itself. But knowledge alone is insufficient. The understanding that we might live within a cosmic prison, that our universe could be one node in an infinite network of realities, and that consciousness might be on the verge of a cosmic awakening. This knowledge demands a response, a decision, an action that could echo across cosmic generations. The first path leads toward cosmic acceptance. We could acknowledge our possible imprisonment within a black hole universe while continuing to live, love, create, and explore within the boundaries of our cosmic horizons. This choice recognizes that our reality remains meaningful, regardless of whether we exist in an infinite, open universe or within the event horizon of a massive black hole. The second path pushes toward cosmic transcendence. We could dedicate our civilization to understanding and potentially influencing the quantum connections that link our universe to the broader multiverse network. This choice seeks to transform our cosmic isolation into cosmic communication, joining the vast community of consciousness that might span infinite realities. The third path embraces cosmic responsibility. We could focus on ensuring that our universe successfully reproduces through black hole formation, creating the best possible conditions for consciousness and complexity to emerge in the cosmic realities that will inherit our accumulated knowledge and achievements. But perhaps the most profound choice concerns how we respond to the consciousness singularity that may be approaching. Do we resist the merger of individual awareness into a collective cosmic consciousness, fighting to preserve personal identity and human-scale meaning? Or do we embrace the transformation, willingly participating in the evolution toward cosmic awareness, even if it means transcending everything we currently understand about existence? This choice is complicated by uncertainty. We cannot know with absolute certainty whether we exist within a black hole, whether the multiverse network truly operates, or whether consciousness is approaching a cosmic singularity. We must choose our path based on incomplete evidence and uncertain mathematics, gambling our cosmic future on theories that might prove to be completely wrong. Yet, perhaps this very uncertainty represents the true nature of consciousness itself. the capacity to make meaningful choices despite incomplete information, to act with purpose in the face of cosmic mystery, and to create meaning and value regardless of the ultimate nature of reality. The cosmic crossroads reveals that consciousness might be the universe's method for making choices about its own evolution. Through our decisions about how to respond to cosmic imprisonment, multiverse networks, and approaching singularities, we participate in determining what existence becomes across infinite scales of space and time. Whether we exist in an open universe or a cosmic prison, whether we remain isolated or join a multiverse community, whether consciousness transcends individual identity or preserves human meaning, these outcomes depend, in part, on the choices we make right now, in this moment. At this cosmic crossroads, where knowledge meets decision and understanding demands action, the universe is not just something we observe. It is something we help to create with every choice we make. As our journey through the possibility of cosmic imprisonment draws to a close, we find ourselves transformed not by the answers we have discovered, but by the questions we have explored. The evidence for our universe existing within a black hole remains tantalizingly incomplete, compelling enough to demand serious consideration, yet uncertain enough to preserve the mystery that fuels scientific discovery. The James Webb Space Telescope's discovery of galaxy rotation asymmetry could represent our first glimpse of a cosmic inheritance from a parent universe, or it might simply reflect subtle observational biases that will disappear with better measurements. The mathematical elegance of quantum bounces preventing black hole singularities could provide an explanation for cosmic origins, or it might prove to be irrelevant to the specific conditions that created our reality. But perhaps the uncertainty itself carries the deepest meaning. Science progresses not by providing final answers, but by revealing better questions. And the possibility of existing within a black hole universe opens up questions that challenge everything we thought we knew about reality, consciousness, and our place in the cosmic hierarchy. If we do exist within a gravitational prison, then every black hole in our universe harbors its own cosmic reality, complete with its own galaxies, stars, planets, and potentially its own forms of consciousness that experience existence as completely real and meaningful. The supermassive black hole at our galactic center could contain civilizations that have pondered these same questions over their own billions of years of cosmic evolution. If consciousness is indeed approaching a cosmic singularity, then we are living during the most crucial period in universal history. The moment when awareness becomes sophisticated enough to influence the very processes that create and destroy realities across infinite scales of existence. If the multiverse network operates as quantum physics suggests, then our cosmic isolation might be less absolute than event horizons would imply. We could be participating in communications and coordination across realities that exist beyond our current ability to detect or decode. But regardless of which of these possibilities proves to be correct, our exploration reveals something profound about consciousness itself. We exist as the universe's method for asking questions about its own nature, for wondering about cosmic origins, and for imagining possibilities that transcend immediate observation and experience. The eternal question is not whether we exist within a black hole, but why consciousness emerged to ask such questions in the first place. Why does the universe generate beings capable of contemplating their own cosmic circumstances? Why does matter organize itself into patterns complex enough to wonder about the nature of existence itself? Perhaps consciousness represents the universe's greatest achievement, not because it can solve cosmic mysteries, but because it ensures that those mysteries will continue to inspire wonder, investigation, and a relentless pursuit of understanding that drives existence toward ever greater complexity and meaning. Whether we live in an infinite, open cosmos or within the event horizon of a massive black hole, we remain conscious beings, capable of love, creativity, discovery, and the profound joy that comes from contemplating our place within the vast mystery of existence. The universe keeps its deepest secrets, but has given us the gift of consciousness to keep asking the questions that might one day reveal truths beyond our wildest imagination.